Welcome, everyone. I'm really glad you're here today for this session on Geographic Information Systems, or GIS, at the introductory level. Whether you're completely new to GIS, or you've heard the term before but never really dug into what it means, this session is designed for you. By the end of our time together, you're going to walk away with a solid foundational understanding of what GIS is, what kinds of data it uses, how maps are made, and what it means to make a good map versus just any map. This presentation is based on MIT's GIS Level 1 workshop material, and it's been used to introduce thousands of students, researchers, and professionals to the world of spatial data. So let's take a moment before we dive in. Look at this image behind the title. That's a satellite orbiting Earth. And that's really where modern GIS begins. Data collected from space, from the air, from the ground, all of it coming together in a system that lets us ask and answer questions about place. Where are things? Why are they there? What patterns exist across geography? How are things changing over time? Those are the kinds of questions GIS helps us answer. And by the end of the session, you'll have the vocabulary and conceptual framework to start exploring those questions yourself. Let's get into it. Here's our roadmap for today. We're going to move through 5 major areas. First, we'll start with the introduction. What is GIS, really? We'll define it, look at the theory behind it, and understand why it matters. Second, we'll look at software options because GIS isn't just one tool. There's a whole ecosystem of software, and we'll help you understand which tool is right for which job. Third, we'll cover GIS applications. What can you actually do with GIS? We'll look at real examples. Fourth, and this is where we'll spend a lot of time, we'll dig into understanding maps and data. This includes data layers, spatial data types like vector and raster, characteristics of spatial data like resolution and scale, and metadata. And fifth, we'll close with making great maps, the principles of cartographic design and data visualization. There's also a take-home exercise at the end that you can complete on your own to practice everything we talk about today. All right, let's start at the beginning. This section is called Introduction, and the big question we're going to answer here is, what is GIS? You might have encountered this acronym before. Maybe you've seen it in a job posting, a research paper, or a news article. Maybe someone on your team uses GIS tools, and you've always wanted to understand what they're doing. Or maybe you've been using Google Maps your whole life, and you're curious what's underneath the hood. Whatever brought you here, great. Let's start from the very beginning. So, what is a geographic information system? The formal definition is this: a system for capturing, storing, checking, integrating, manipulating, analyzing, and displaying spatial data. Let's unpack that slowly, because every word in that definition matters. Capturing, GIS helps us collect data about the world. That data can come from satellites, GPS devices, aerial photography, field surveys, sensors, government records, you name it. Storing, once we have that data, we need somewhere to keep it. GIS involves databases and file systems specifically designed to store geographic information. Checking, this is about data quality. Is the data accurate? Is it current? Does it align with other datasets? GIS tools help us verify and validate our data. Integrating, one of the most powerful things about GIS is that it allows you to bring together multiple datasets from different sources and look at them together. We can overlay a road network on top of an elevation model on top of population data, all at once. Manipulating, we can transform data. We can clip it, buffer it, reproject it, reclassify it. GIS gives us a toolkit to reshape data for our specific needs. Analyzing, this is where the real power lives. We can ask spatial questions. Which areas are within 500 meters of a hospital? Where do flood risk zones overlap with low-income neighborhoods? What's the best route between 2 points? Displaying, and finally, GIS lets us visualize all of this as maps, charts, and reports that communicate our findings to others. So GIS is not just a map-making tool. It is a full analytical system from data collection all the way to communication and decision-making. This slide repeats the definition, but now the key phrase is highlighted: a system for spatial data. Notice that the word spatial is emphasized here. This is the heart of what makes GIS different from any other data management or analysis system. Spatial data is data that has a geographic component. It's connected to a location on Earth. It could be a point, like the location of a hospital. It could be a line, like a road or a river. It could be a polygon, like the boundary of a city or a country. Or it could be a raster grid, like satellite imagery or an elevation model. Because the data is spatial, it can be visualized on a map, and that's what makes GIS so uniquely powerful. When we see patterns in space, we often see things that are invisible in tables and charts. The map reveals relationships. So keep this word in mind throughout the session. Spatial. It's the key to understanding everything we're going to talk about. Now, let's look at how GIS actually works as a system, from input to output. Think of it as a three-stage pipeline. Input, processing, output. At the top, we have input, spatial data. This is the raw material. You bring in data from a variety of sources: shape files, raster images, CSV tables with coordinates, GPS tracks, satellite imagery. GIS doesn't generate this data on its own. It's a tool for working with data that already exists or that you've collected. This is an important point. GIS software does not come with its own data. This is something beginners often misunderstand. They open ArcGIS or QGIS and wonder, where's the map? The answer is, you bring the map. You bring the data. In the middle is the GIS/mapping software, tools like ArcGIS Pro, QGIS, or web-based platforms like ArcGIS Online. This is where analysis happens. You ask questions, run tools, manipulate layers, and build visualizations. At the bottom is output, new data and maps. The result of your GIS work is something new: a map, a report, a new dataset, a spatial analysis, a decision. GIS is a means to an end. The output should always serve a purpose. This pipeline is simple, but important. It frames how you should think about every GIS project. What data do I have? What question do I want to answer? What output do I need? Now, let's get conceptual for a moment. At its core, GIS is about representing the real world digitally. Look at the image in this slide. You have a three-dimensional, complex, messy real world: terrain, water, buildings, roads, people, vegetation. And you want to bring that into a computer so you can analyze it.
How do you do that?
You abstract it.
You simplify it.
You take specific themes from the real world and represent them as data layers. Think about it this way. The real world doesn't come pre-organized into neat categories. But in GIS, we impose structure. We say, here's a layer for elevation. Here's a layer for roads. Here's a layer for land use. Here's a layer for population density. Each layer captures one theme of reality, and by stacking them together, we can start to understand the relationships between them. This slide shows what that looks like visually. Starting from the real world at the top, GIS digitizes that world into themed data layers. Look at the example layers shown here. Customers, points showing where people are located, streets, lines representing the road network parcels, polygons showing land ownership elevation, a raster surface showing terrain height land usage, a classification of how land is used. Each of these layers represents one slice of reality. Now here's the magic. Because they all share the same geographic coordinate system, you can overlay them on top of each other. You can ask, which customers live in parcels that are zoned for commercial use, within 500 meters of a major street, in a low-elevation flood zone? That kind of question, a spatial question, can only be answered when you have these layers working together. This is the fundamental architecture of GIS. It's a layer cake of spatial data. And then you overlay them for analysis. The output at the bottom of this diagram shows the result of combining those layers. This could be a new map, a new dataset, a statistical summary, or a decision support product. This is the theoretical heart of GIS: real-world layers, combination, analysis, insight. Keep this mental model in mind throughout the session. Every tool, every data type, every visualization principle we discussed today feeds back into this core framework. All right, let's move into our second section, software. Now that we understand what GIS is conceptually, let's talk about the tools you'll actually use to do GIS. The software landscape for GIS is broad. There are tools designed for different levels of expertise, different use cases, and different budgets. Let's break it down. We can organize GIS and mapping software into three major categories based on their analysis power: Geobrowsers, web-based tools, and desktop GIS. Geobrowsers are at the low end of analysis power. These are tools like Google Maps, Google Earth, Apple Maps, and Waze. Most of us use these every day. They're fantastic for navigation and displaying information, but they're fundamentally limited. You can't upload your own datasets, run spatial analyses, or control how data is symbolized. They're viewers, not analyzers. Web-based GIS platforms sit in the middle. Tools like Carto, ArcGIS Online, Mapbox, and Google My Maps allow you to upload your own data, customize how it looks, and perform some basic analyses. These are accessible. You don't need to install anything, and they're great for sharing maps online. But they're still limited compared to desktop tools when it comes to advanced analysis. Desktop GIS software is where the full power of GIS lives. These are installed applications. ArcGIS Pro and QGIS are the two most widely used. Desktop GIS gives you complete control over your data, your analysis, and your map output. You can run complex spatial algorithms, manage large geodatabases, and produce publication-quality cartography. For most serious GIS work, research, environmental analysis, urban planning, hazard mapping, and so on, you'll be working in desktop GIS. So within desktop GIS, which should you choose? ArcGIS Pro or QGIS? This is a genuinely important question, and the honest answer is, it depends on your situation. Let's look at both side by side. ArcGIS Pro, made by GIS, is the industry standard in many professional and government contexts. Here's what you need to know about it. It's commercial software, meaning it costs money. Individual licenses can be expensive, though many universities and organizations have institutional licenses that give students and researchers free or discounted access. It only runs on Windows. If you're on a Mac or Linux, you'll need a workaround. It can be a larger program and may run slowly on older computers. But on the positive side, it has a full, mature set of GIS tools covering everything from basic mapping to advanced 3D analysis, geostatistics, and machine learning integration. It integrates seamlessly with ArcGIS Online, which is great for web publishing. And it has an excellent training ecosystem. GIS offers official documentation, video tutorials, and MOOCs, massive open online courses that are genuinely high quality. Support is professional and comprehensive. Now for QGIS. It's completely free and open source. This is a major advantage, especially for students and researchers in resource-constrained settings. It runs on any operating system: Windows, Mac, Linux. It's a lighter program that won't bog down your machine. It has a large library of plugins contributed by the open-source community, which extends its functionality considerably. However, it does lack some specific tools, particularly for network analysis and spatial statistics, that ArcGIS Pro handles natively. Documentation and support can be inconsistent, since plugins are developed by many different contributors with varying levels of rigor. My recommendation: if you have access to ArcGIS Pro through your institution, use it for professional work. If you need a free, cross-platform option, or if you're working in open-source environments, QGIS is an excellent choice. Many GIS professionals use both. The first application is viewing imagery. GIS allows you to load, display, and work with aerial and satellite imagery. The image in this slide shows an aerial photograph of the city of Cambridge, Massachusetts, taken in April 2010. This kind of imagery is an incredibly rich source of spatial information. You can see roads, buildings, vegetation, water bodies, land cover, all captured from above. In GIS, imagery is treated as a raster layer. We'll get into what that means in detail shortly. You can drape other data layers on top of imagery, use it as a base map, or analyze it directly to extract information about what's on the ground. Remote sensing, the science of extracting information from imagery, is a deep field in its own right. If you're working with satellite data like Landsat, Sentinel, or MODIS, you're doing remote sensing within a GIS framework. That's a topic worth diving into on its own. GIS can also be used to create 3D models of the built and natural environment. The images here show 3D building models. You can see city blocks extruded into 3 dimensions, showing building heights, footprints, and spatial relationships. This kind of 3D GIS analysis is used in urban planning, shadow analysis, line-of-sight calculations, flood modeling, and environmental impact assessments. Tools like ArcGIS Pro have native 3D capabilities. There are also specialized software platforms like AutoCAD, Rhino, and Agisoft Metashape that are used for more detailed 3D modeling and photogrammetry, and the outputs from those tools can be brought into GIS for spatial analysis. Of course, one of the most classic applications of GIS is creating maps. The example here shows a choropleth map of Irish ancestry across U.S. counties from the 2009 to 2013 American Community Survey. Each county is shaded based on the percentage of the population that identifies as having Irish ancestry. What I love about this example is how it illustrates a simple but profound idea. Maps combine art and science. The science is the data, census figures, geographic boundaries, statistical classification. The art is the design, the color choice, the classification method, the layout, the typography, the legend. A great map is both accurate and beautiful. It communicates a clear message to a specific audience. And making great maps is a skill that takes practice, which is why we'll dedicate a significant portion of this session to cartographic principles. And perhaps most powerfully, GIS lets you conduct spatial analyses. Look at the 3 examples on this slide. Spatial statistics. The map on the upper right shows crime hotspot analysis. By looking at where incidents cluster in space, we can identify patterns that aren't visible in a simple table of data. This is the basis for much public safety analysis, epidemiology, and environmental justice research. Buffer tool. The concentric rings in the lower middle show a buffer analysis. You pick a location, say a train station, and you create rings at 500 m, 1 kilometer, 2 kilometers. Now you can ask, how many residents live within walking distance? How many businesses? How many schools? Clip tool. The upper left shows a state boundary clipped to a smaller extent. When you're working with large national datasets but only need a specific region, you clip the data to your study area. This saves processing time and keeps your workspace clean. These are just 3 examples. GIS has hundreds of analytical tools: overlay, interpolation, network analysis, raster algebra, terrain analysis, and much more. We'll touch on some of these in GIS Level 2. Here's a question to get us thinking. Look at this Google Maps screenshot of Cambridge, Massachusetts, near MIT. What individual data layers were used to create this map?
Take a moment.
Look carefully. What distinct types of information can you identify?
You can see streets,
Water, green spaces, labels, icons, transit markers. Each of those is a separate data layer. Google didn't create one unified map. They created many separate datasets and stacked them together. Here's the answer. Street network. All the roads and paths, represented as lines. Parks and other open space. Green polygons representing recreational areas and open land. T-stops with labels. Points representing transit stations with text labels. Bodies of water. Polygons representing rivers, ponds, and the Charles River. Points of interest. Icons representing businesses, landmarks, museums, and other named places. And there's a note at the bottom. Google Maps is a Geobrowser, meaning it's powerful for displaying these layers, but you can't access or modify the underlying data. You're a consumer, not an analyst. In a real GIS environment, you would have access to each of these individual layers. You could turn them on and off, symbolize them differently, add new layers, and perform analysis across them. This is the fundamental shift from using a map to making and analyzing with maps. All geospatial data falls into one of 2 categories. Vector data, represented as points, lines, and polygons. Raster data, represented as a grid of rows and columns, pixels. Both formats represent the same real world, but in fundamentally different ways, and each is better suited to certain types of phenomena. Think about it this way. If you want to represent a city boundary, a vector polygon is natural. It has a clear, defined edge. But if you want to represent temperature across a landscape, a raster grid makes more sense. Temperature varies continuously across space, with no hard boundaries. We're going to look at both in detail. Here's a simple illustration of the difference. On the left side, you see the letter A drawn as a vector. Notice how smooth and crisp the curves are. That's because vectors are defined by coordinates, mathematical points, and the curves or lines that connect them. No matter how much you zoom in, a vector shape remains perfectly smooth. On the right side, you see the same letter, A, represented as a raster. It looks pixelated because rasters are grids of pixels, and each pixel has a single value. When you zoom in on a raster, you start to see the individual cells. This is the fundamental trade-off. Vectors are precise and scale well, but they represent discrete objects. Rasters can represent continuous surfaces, but they have a fixed resolution. The bottom text summarizes the use cases. Vectors are typically used for features with defined borders, things made by humans like roads, buildings, administrative boundaries. Rasters are typically used for continuous surfaces, environmental variables like elevation, temperature, rainfall, land cover. Let's look at vector data in practice. The 4 panels here show the same geographic area, the Boston/Massachusetts Transit Network, represented using different vector geometry types. Points, individual locations like train stations or bus stops. Lines, the transit routes connecting those stations. Polygons, administrative boundaries like towns or counties. Combined, when you overlay all 3 geometry types together, you get the full picture, colored routes running through municipalities, with stations marked as points. This is the power of the layer approach. Each geometry type captures a different aspect of the same geographic reality, and together they tell a complete story. Now, let's look more closely at how vector data is structured. Every vector dataset has 2 components, a front end and a back end. The front end is the geometry, what you see on the map. In this example, the geometry consists of state polygons, the shapes of states in New England. When you look at a vector map, you're looking at the front end. The polygons, lines, and points that are rendered on screen are the visual representation of coordinate data stored in the file. The back end is the attribute table, the database that lives behind every vector layer. Look at the table in this slide. It shows data for the New England states. Each row represents one geographic feature. In this case, one state. Vermont is in row 0. Connecticut is in row 1. Massachusetts is in row 2.
And so on.
Each column represents a variable, an attribute of that feature. Here we have FID, the unique identifier, shape, the geometry type, name, the state name, and pop_PER_SQMI, population density per square mile. Crucially, the number of columns is theoretically unlimited. You can attach as many variables as you want to each geographic feature. You could add median income, elevation, area, political affiliation, flood risk, anything. This combination of geometry, the shape, and attributes, the data, is what makes vector GIS so powerful. You're not just mapping shapes, you're mapping information. Here's an example of how you can use the attribute table to control what the map looks like. In this slide, each state is symbolized by the name column, a qualitative, categorical variable. Each state gets a different color to distinguish it from its neighbors. There's no numerical ordering. Maine isn't more than Vermont. The colors are just labels. This is appropriate for qualitative data, categories, names, types, classifications. Now here's the same states symbolized by the pop_PER_SQMI column, population density per square mile. This is a quantitative, numerical variable. Now the colors have meaning. Darker means more densely populated. Lighter means less populated. Rhode Island, being the smallest but most densely packed state, appears darkest. Maine, being large and sparsely populated, appears lightest. This is the power of GIS visualization. By changing the variable you symbolize, you completely change the story the map tells. Same geography, same data file, completely different communication depending on which column you choose to display. Let's talk about file formats for vector data. The most common vector file format you'll encounter is the shapefile. Developed by Esri, the shapefile has been the industry standard for decades. Here's something that trips up beginners: A shapefile is not actually a single file. It's a collection of multiple files that all share the same name but have different extensions. The shop, the geometry, the shapes themselves, SHX, a spatial index that speeds up rendering, SPX, another index file, DBF, the attribute table, the database, the PRJ, the projection information, how the coordinates map to Earth's surface. All of these files must stay together. If you move a shapefile and leave the .prj behind, GIS won't know what coordinate system you're using. If you lose the .dbf, you lose all your attribute data. Keep them in the same folder, always. When you load a shapefile into ArcGIS Pro or QGIS, you'll see just one entry in your layer list. The software handles the multi-file structure behind the scenes. Now, let's shift to raster data. Raster data represents the world as a grid of cells, like a digital image. Each cell has a value. The collection of those values across the grid forms a continuous surface. Raster data includes aerial photographs, visual imagery captured from aircraft digital elevation models, DEMs, grids where each cell contains a height value scan maps, paper maps digitized into raster format satellite imagery, multispectral data from sensors like Landsat or Sentinel classified land cover maps, grids where each cell is labeled with a land use category. The key reminder: rasters are grids of pixels. The spatial resolution of a raster is defined by the size of each pixel. A 10-meter resolution raster means each pixel represents a 10m times 10m area on the ground. Just like vector data has a front end and back end, raster data does too. The front end of a raster is the cell matrix, the visible grid of pixels you see on the map. Some important properties. Each cell has its own value. A raster can only display one variable at a time, unlike a vector layer, which can store many attributes in its table. This means if you have a DEM, elevation, raster, and a temperature raster, those are two separate raster files. You can analyze them together, but you can't store elevation and temperature in the same raster simultaneously. Here's what a raster looks like, symbolized by elevation values. The darker areas represent lower elevations. Lighter areas represent higher ground. This is a DEM, a digital elevation model, of the New England states. Notice how the color gradient conveys a continuous surface. There are no sharp edges, except at coastlines and political boundaries. Elevation flows gradually across the landscape. This is fundamentally different from a vector polygon map, where you'd have distinct, separate shapes. The raster captures the spatial continuity of the terrain.